Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a pleasure to have Aram Harrow. He got his PhD at MIT, as he told me, and then was professor in Bristol, and now he's at UW. And he's brave enough to give a Blackboard talk today.
Thanks. So I want to tell you about some quantum stuff I've been working on, but I'll describe it in a way where it doesn't sound quantum at all. It's a problem which doesn't have to be quantum. Like, you could solve it with totally non-quantum techniques. But bizarrely, it happens that most of the progress that's been made on it, at least from my subjective point of view, but I think objectively has been quantum. So what is the problem? Well, we're given a tensor, aijk, where I, j, and k range from 1 to n. And we want to compute an analog of the largest singular value of this tensor. And this thing is called the injective tensor norm. And it's related to a way of defining norms on Banach spaces. And that's actually totally irrelevant to what I'm going to talk about. So we're going to need that only as far as the name. And what the thing is the following. It's the maximum over unit vectors of this quantity. So if the third dimension didn't exist, this would just be the largest singular value. And it's so that's why you can think of it as a generalization of the largest singular value. And there's a few other ways you can think about it. So if you drop, so you can think of it as simply a maximum over x and y. And whenever I write x and y from now on, they're going to be unit vectors. So I'll stop writing all the conditions. Of ijk So instead of the maximum of a number, we can think of it as the maximum norm of a vector. So ek is the unit vector.
There's no summing over k? What is?
Oh, sorry. Yeah, thanks. Thanks. Right, I'm summing over k, but z has gone away, but k hasn't. Thanks. Right. I mean, the reason why this is true is just because the maximum inner product of a vector with another unit vector is the norm of that vector. And you could further write it as simply the maximum over x of the operator norm of a matrix. Where this norm, operator norm means largest singular value. So it has these different interpretations, and which is related to the flexibility of a tensor. So a tensor you can think of as, a single vector of length n cubed. You can think of it as a linear map from vectors of length n to matrices. You can think of it as a trilinear form. All these different interpretations you can move between. So I guess in this talk, what I want to do, I want to spend the first part giving you a few more equivalences. And I'll reduce it to a form which is a little more congenial to work with. And then I'll talk about an application to planted clique. And then I'll tell you about various quantum results related to it. One of the quantum results is one paper I'm on. Some of the others are not. The quantum results all basically give you results about the hardness of this problem. And I like them because the first instinct of many people is I think something I heard Bela tell me a few weeks ago when I told him I was thinking about the hardness of this problem. He said, nobody works on that. It's too unstructured. There's no structure there. And naively, it really, it looks really quite general. But it turns out that there is a fair amount you can say about this problem. OK, so the way we'll attack it, I want to focus on this interpretation for now. And I want to make it look like a convex optimization. So the way to do that will be sort of like the way you can write, if you have a normal matrix M, if you want to write the largest singular value of M, you can think of it as the square root of the largest eigenvalue of M star M. So we can do something similar here. We can say that the square of this norm is equal to the max over xy of this quantity squared. And if you write out this quantity squared, it's simply sum over I1, I2, J1, J2, sum over k, A, I1, J1, k bar, A, I2, J2k, xi1 bar, xi2, yj1 bar, yj2. Looks pretty horrifying, but it turns out this is about to get very simple. Because the first thing we can do is we can separate out the part of the input. So that's this thing here. And let's call this a big matrix B. And let's have the matrix be n squared by n squared. So it's indexed by I1, J1, and I2, J2. And when you do it in this way, this has the form of A star A. So in particular, B is positive definite, and the and Hermitian, and the operator norm of B is equal to, let me say it in words first. We can think of A as a map from the K index, which is an n-dimensional space, to the ij indices together. Sorry, K is n-dimensional, and to the ij indices, which are n-squared dimensional. And B, in that picture, B is just A star A. So the operator norm of B is equal to the square of the operator norm of A when we view it as a matrix that's n by n squared. So B is a rather simple thing. The other nice thing about this is, so let's assume that this is less than or equal to 1. It's just an overall normalization. It's the one that I'm going to work with. It's an if and only. I mean, it goes back and forth. So if you take B to be any matrix satisfying these, you can construct a corresponding A for which this appears, just like you can take the square root of any matrix. OK, so that's this side. What about these x's and y's? So we can write this maximization. So this thing here equals the max over x and y. Well, this is really bad board technique. This is equal to the maximum over x and y of the trace of B times a matrix depending on the x's. And what's that matrix going to be? It'll be x, x star, tensor y, y star. And what this tensor product means is, so if you have matrices x, tensor y, this is equal to the block matrix x11 times y, x12 times y, x21 times y, and so on. So this thing is indexed by I1, I2, for example. So this is indexed by I1, I2, and this is indexed by J1, J2, and the whole thing is indexed by I1, J1, I2, J2. OK, so so this is almost like a convex optimization problem. And to make it a convex optimization problem, we'll turn this into a convex set. So this set right now is definitely not convex. For example, if you were to get rid of the y's, this would just be the set of rank 1 projectors, which is definitely not convex. But the convex hull of it is. So let's define the convex hull of this set. And I'll let the dimensions perhaps be different. And they're still unit vectors. So this set, using quantum notation, we'll say this is a set of separable density matrices. So in quantum land, this is the set of states where one party has n1 dimensions and the second party has n2 dimensions, and they don't have any entanglement. They're allowed to have classical correlated probability distributions, or classical correlations between their states, but no entanglement. So what this problem is now is I want to introduce one more piece of notation, which is if K is a convex set, then the support function of K is h sub K, and it's equal to the maximum of the inner product of x and y, where y is in K. And for matrices, we define the inner product according to the trace. So using this notation, we can now say that this quantity is basically evaluating the support function of sep n comma n of B. So why is that? We're optimizing the trace of B times some element of the set of separable, some element of this set. And the reason why we can replace this thing with the convex hull of all of those is because it's a linear function on that set. So what does this mean? This means if we're interested in these tensor problems, it turns into a problem of working with this set. And one immediate corollary comes from the fact that optimizing a linear function over a convex set is equivalent to determining membership in that set. So it's just as hard to determine, modulo some epsilons, which I won't get into right now. It's just as hard to calculate these tensor norms as it is to determine membership in this set of matrices, which is something that may seem to you like an even more obscure problem, but quantum people have worked on this, and there's some partial results on this. OK, so fine. So why do we care about these tensors? One application is to the planted clique problem. Maybe I'll briefly say what that is. So let's say you have a graph on n vertices, and we'll define the matrix Eij is 1 if there's an edge from I, or between I and j, and 0 if not. And our model of a random graph will be to just independently place an edge with probability 1/2 at between each pair, and so edge with probability 1/2, no edge with probability 1/2. And the planted clique model, the planted clique problem, is I choose m vertices and connect edges between all of them. And then choose the remaining edges to either be present or absent with probability 1/2. And the problem is distinguish a graph with a planted clique from without a planted clique. And the problem is parameterized by m and n. And obviously, as m gets bigger, the problem gets easier. If m were equal to n minus 1, it'd be very easy. And it turns out that if m is bigger than actually some constant times root n, I believe. Is that right? It becomes our best algorithms work when m is bigger than a constant times root n.
Right. But when you say work, you mean
Polytime.
Polytime, right? So
Yeah. So if m is actually, so this is a question I don't know. Suppose m is equal to n to the 0.49. Then do we have an algorithm that's sort of less than 2 to the n for that?
yeah, n to the log n. Quasi-polynomial.
OK. And it's quasi-polynomial down to m equals what?
2 log n. So, I mean,
I see.
Down to the cliques that appear, 2 log n is already appearing in the.
Right, right. So 2, yeah. So I should say, even with no planted clique, you'll have a clique of size 2 log n. I see. So in quasi-polytime, you could even do 2 log n plus 5 or something. I see. So, right. So this problem is substantially easier than the worst case of clique, which is NP complete. And it was shown by Brubacher and Vempala in the paper 09052381. Actually, I mean, this is the arXiv number.
We don't do that here.
Well, you can search Brubacher Vempala. You what?
Imaginative type.
Yeah. Well, it's informative, right? At least the first 4 digits tell you when it came out. So, I mean, the idea is originally to do it a Fries and Canaan, but this is the most recent paper on the subject. So a good place to start reading if you were to look into it.
How do you memorize?
Oh, I wrote it down. Some of them, my own papers, I memorized. So the paper I'm going to talk about, my paper, we tried to get the first paper of 2010, and I was doing something for New Year's that my co-author was slow on the trigger, and so we got the 17th paper. But that I can definitely remember.
Instead of talking, you can just write down the list of numbers.
Yeah, right. Well, this joke about there's these prisoners, and they say, yeah, can't do an Irish accent, worth the damn. So, OK, so what is the relation between planted clique and this problem? Well, you define the tensor as follows. Aijk is equal to -1 is basically the parity of the number of edges in a triangle if I, j, and k are distinct. I think this qualifier is a little unnecessary. And 0 otherwise. So if some I equals j or I equals k, whatever, you set this to 0. But otherwise, you set it to be this weird parity. And the adjacency matrix, because I already took A. So it's E. OK, so what's the point of this? Well, suppose you have a planted clique. Suppose there's a clique. Then let's set x to be 1 over root m on the vertices in the clique, and 0 elsewhere. So it's a unit. There are m vertices in the clique, so this is a unit vector. And it has a property that when you apply it to A, all of these entries will be -1. So when you do this absolute value, you'll get, so if there's a clique of size m, so clique of size m, means that there's a vector that achieves that this thing is greater than or equal to, with up to a constant factor, m to the 3/2. Because there's m cubed terms that all contribute of -1. Doesn't matter if it's plus or -1, as long as it's the same sign. And each term is weighted by 1 over m to the 3/2. So that's if there is a clique of size m. What if there's no clique? So that's where they have to actually do work in this paper, show that for a random graph with high probability, this thing should be small. And what it is that it's order root n. In fact, what they do is a little bit more. What they show, they actually consider the version with r indices. So you have ai1 through air equals -1 to the sum over I, all pairs between 1 and r of, I can use different indices, j, k, ei, j, I, k. So it's just, this is where 3 indices, just generalize it to r indices. And then they find that if there's a clique, then this thing is bigger than m to the r over 2. And if there's no clique, this is less than or equal to still root n, but now there's a factor of r log n to the order r. So if you think of r as pretty small, this is still more or less root n, and then this gets better and better. And so what it means is that if you could solve this thing, then the points where these cross is when m is like n to the 1 over r. So when r is 2, that's our existing algorithm, up to these log factors. When r is, I guess, when you put in the log factors, you go from a difficult algorithm to a really trivial algorithm, but it's the stuff we can do. But when r is 3, that's more than we know how to do already. So if you'd solve this tensor problem, you'd solve something we didn't know how to solve before. And what I can almost show is that if you could solve a tensor problem with the right parameters for this, you could do stuff that's a lot harder. I can't quite show that, but I'll tell you what I can do. So I'd like to translate this into this language now. And to do this, I want to sort of set the right scale. So I want to talk about the operator norm of, let's just stick with 3 indices. So the question is, what is the operator norm of A as an n by n squared matrix? Yeah?
So could I just ask, can you shed any light on why it's -1 to the power of this? Does this somehow make things magically cancel out in the random graph case?
Yeah, I haven't actually read their proof in great detail, but the point is, if there's no clique, these things should be pointing in different directions. So if there's a clique, then all the signs come out the same way. And then, so one way of thinking about it, I think the way the proof works is it's your basic epsilon net sort of thing. So, and then what you want to do is you want to take an epsilon net over all vectors x, y, and z. And then let's restrict actually to the case when x, y, and z are flat. So suppose you can decompose x into a sum of things where everything's kind of you have got a bunch of terms that are all about the same magnitude and then a bunch of zeros. So you're basically looking at subsets of your graph. And then, so you look at what this corresponds to is it's sort of like taking rectangular sections. And then if you fix some rectangular section and then take a random graph, you've got a bunch of cancellations. That's pretty much the intuition. And then it's your usual race of exponentials. You've got your epsilon nets versus your concentration function. And then they have some very careful concentration of measure arguments, and that's how the proof goes. And I forget exactly what is their concentration of measure contribution. It's something that's where they have to do their work. But that's the intuition. So let me tell you one thing I haven't worked out, but I think there would follow from their results. So what is the operator norm of this thing? I didn't actually do the proof for this. I just did numerics. And the numerics are extremely convincing. I guess in this audience, you guys also use numerics, so there won't be any, and you're not carrying any tomatoes. So what I can say, what I can say is that this operator norm is about n, or order n. And yeah, so what does this even mean? This means you group together two indices, so this becomes an n by n squared matrix. And it's a plus or minus 1 matrix. So even a single row has norm n. Because a single row has n squared entries, each plus or minus 1. So there's norm roughly n. So if all of these rows were orthogonal, then the whole thing would have norm, operator norm n. And that's sort of what units would say, and that's also what the numerics say. So let's suppose that's true now. Then what we have is, so we construct the matrix B. B will be, you could say it's sort of A, ij, k, star times A, ij, k, and then let's divide by n squared. So that,
Same with the
yeah, same as that's my shorthand for doing this. Basically,
the A that you're using is the same you used before.
this A is from here. So, but now I want to divide, so I make this normalized. So now B has a property that the operator norm of B is less than 1.
And it's not only the random graphs of the edges or
Random. Yeah. Oh, yeah, yeah. So if there's no clique, then this is true. And if there's no clique, then this is true. I think a clique wouldn't change this a whole lot, though. I haven't worked that out, but when I last thought about this, I believe the clique wouldn't change it by very much. At least a clique of size n to the 1/3. So what this is now, we want to distinguish the two cases. And so what happens is that if there's a clique, so I've said that the injective tensor norm squared is this thing. So in this notation, clique means that h, can you read this corner here? No. So clique means that h sep of n comma n of b is greater than or equal to m cubed over n squared. I'm neglecting constant factors. And no clique means that this quantity is less than or equal to 1 over n. So, again, when m is bigger than n to the 1/3, then you get a real separation. And so if m, and in particular, and so what you'd like to be able to do is figure out whether this quantity is, say, less than 1 over n or greater than 2 over n. That's pretty much the problem that we want to be able to solve, is distinguishing those two cases. So, no, I will in a sec. Yeah. Which is good, because I'm about to change topics. Now,
also known as hidden clique.
Not just planted clique, but hidden clique.
Both names are used, but I thought that's why you're writing in small versus.
Oh, I see. Oh my God, yeah. How can anyone read that?
It's supposed to be hidden.
Yeah. Well, hidden clique is like writing on Alexandra's whiteboard, where whatever words I add, there's this constant backdrop of previous whiteboard markers, which are randomly either present or absent. Okay, so that's one reason we'd like to know this. So let me tell you now some actual results. And the first result is not due to me. It's due to 0804.0802, otherwise known as the power of unentanglement by Aronson, Drucker, Pfefferman, Shor, and someone else like Beiji. Usually just called Aronson et al. But I think this part is due to Shor. So what is the result? The result is, suppose, actually I'll introduce one more piece of notation. So this is SEP on n comma n. So let's suppose we have actually several systems, not just two, but k systems. So this is the case, when you have k tensors. I'm just going to call this SEP to the k of n. So our old thing was SEP to the 2 of n. So what they showed is the following. When k, suppose you take k to be order root n, and I'm suppressing some polylogs here. Maybe I'll put those in. Actually, let's do this. Let's say n is equal to m polylog m. And now what we have, should I be writing bigger still, or is this OK? What we have is a 3-sat formula phi with m variables and order m clauses. What the result is that you can encode phi into one of these tensor problems. So there exists b and of size n to the k. So PSD means a set of positive semi-definite matrices. So there exists a big B whose operator norm is equal to 1 or less than equal to 1. Such that if phi is satisfiable, then this quantity will equal 1. And if phi is unsatisfiable, then this quantity will be less than a half. So sometimes we call this the completeness and this the soundness. There's a quantum interpretation of this, which is that you have k quantum provers, each sending you log n qubits. And the provers are guaranteed to send you unentangled things. That's why you have these separable states. And then you make some measurement. If the thing is satisfiable, you always output yes. If it's unsatisfiable, you output yes with probability at most a half. So that's why quantum people have been looking at this. And one consequence of this is, so this set is optimizing its matrices of dimension n to the n to the k. So you might think you could optimize over it in time polynomial in that. And this says you can't do that, not even to constant accuracy. So it says that if you had a poly n to the k algorithm to estimate h, this quantity, plus or minus some constant error, 0.1. If you could do that, then n to the k here is like n to the root n. So we would say you could solve 3-sat in time n to the root n, which we don't believe is possible. Then that would imply that 3-sat instances of size m would be contained in time exp root m polylog m. So Not quite p equals np, but pretty unlikely. So that is, I think, the first real hardness result of the problem. It says, OK, well, not for the case of 3-index tensors, but for like tensors with a ton of indices, you can't solve it in time polynomial linear input. OK, so maybe I shouldn't erase this part. It's OK. Does anyone object to me erasing this part? So what if you have 3 indices? I mean, that's the case that this k indices. Who knows what that means? That's a problem that we haven't thought about very much. 3 indices seems a little bit more basic. So how hard is that problem? So it turns out that so what we want to compute is h sep squared of n up to some error epsilon. So it turns out that 3 sat of length n can be solved or reduced to this class with if these parameters no longer have a constant gap. C equals 1, S equals 1 minus 1 over a little more than n cubed. So determining this to very high precision is hard. And this is due to 0810.5109, also known as a paper by Salman Begi. And this same result has been rederived many, many times. Each time, because at the beginning I wrote down all those different equivalences. Each time people proving this hardness about a different result, different one of the equivalences. I think the first proof was in 2002. But this one has slightly better parameters. So that's fine to this if you want to get it to super high precision. But what about to constant accuracy? I mean, that's the case we care about a little bit more. Although actually, yeah, this one already is a little bit troubling for that case. I mean, it's in a sense, you could think of this as constant multiplicative error or as 1 over n additive error. So one result, so the result that I have, which actually I obtained this result together with Ashley Montanaro before we even knew anything about tensors or anything. This is sort of what led us to think about all these other problems, is that there's a reduction from the k-index case to the 2-index case. So this is this paper, otherwise known as Montanaro. And what we found is that for any b that's n dimension n to the k by n to the k, there exists some matrix C that's a little bit bigger, but the quantity we're interested in, so 1 minus, so this is the quantity that before we wanted to approximate. How close is this thing to 1? That this is more or less approximated by the same thing for C. But now C we can interpret as as being separable across a cut of 2 systems rather than K. So B, we're optimizing against a tensor product of K things. C, we're optimizing over tensor product of 2 things. And this thing here means that they're related by constant factors in both directions. And constructing C from B is very easy. you just write its the constructions of this form. So you take B, tensor product it with a big identity matrix, and sandwich the whole thing by some projector pi. And pi is the span of vectors of this form. And let me give you a little intuition why this is true. The details are annoying, but the big picture is not that bad. The idea is that this B that we're testing, we want to optimize it against things that are product across k indices. So let's say k is 5. We've got these 5 systems here. And what we do is, for C, we double it, basically. We consider 5 more systems. And we're optimizing across things that are product across this cut. Because it's a tensor product of things that are, XX star here, tensor YY star here. And we want this to approximate things that are, we'd like things to be product across these 5 systems. And so what we do is we project onto the space. What we do is we really ask for 2 copies of the proof. So the proof would be like, V1, tensor V2, tensor V3, tensor V4, tensor V5. We say, look, I'd like 2 copies. I want you to give me 1 up here and then 1 down here. So I'm thinking of this as something where there's a prover who's trying to convince, I'm gonna test trace B against whatever gets sent to me, or trace C against whatever gets sent to me, and the prover's trying to maximize, by choosing something in here that's going to maximize that inner product. And in the original problem, they're allowed to choose something of this form. And the new problem, they're allowed to choose totally arbitrary state up here and totally arbitrary state here, but at least they have to be product across this cut. And then what I do is I say, well, these are the states that I want, and I'm going to project onto the span of all of those states. So that's what this pi does. It says, allow anything that's a linear combination of those states. And it turns out that gives you a reasonable approximation. Going from the set of all those states to their span doesn't give them that much opportunity for cheating. There's, as for why that's true, there's details, but that's sort of the idea. So what you do is you first test, is the state even of the right form? Then once you're convinced it's of the right form, you can just test one of these against your original state B. Think of B as your first test. And once you know that your states are of the desired form, you apply B to some of those. So that's why this works. And what does that mean? That means that we can take this 3-sat formula, create this test, and then turn it into something that's a 2-index test. So that means that distinguishing whether h sep 2 of n to the 2k is bigger than, actually, let's say n to the 2 root n is either equal to 1 or less than 1/2. And I know the constants change, but still you can make this about half again, is at least as hard as a 3-sat instance of length n over polylog n. So we've got the same basic hardness result, but now for SEP2, which corresponds back to 3-index tensors. So constant factor approximation. If you could do that in poly time, then you could solve 3-sat in sub-exponential time. OK, so what does all this have to do with planted clique? So here, we're always talking about completeness 1 and soundness constant, or completeness 1 and soundness almost 1. With planted clique, we have, let's say, completeness 2 over n and soundness 1 over n. So how hard is that? Well, I believe, so basically I don't know. I think that by modifying this construction, you can get that this is as hard as 3-sat. And what that would mean is that this is not actually a very good way of solving planted clique. Because, you can solve 3-sat.
Reduce to a harder problem.
Yeah. So I only started thinking about this last night when I was preparing this talk. And it almost seemed like it was working, but then it didn't quite work. So basically, it's something I'm thinking about now. It feels more like it should work than it shouldn't, but
What should work?
You take the protocol that they did for this. Basically, let me tell you a little bit about the completeness for this protocol. So the reason you're taking k to be root n is you're in fact demanding k copies of the exact same state. And then you're doing some test on it. You're doing something to each one that produces a random outcome between 1 and n. And in order to have a meaningful test, you want to have a birthday collision. And so that's why k has to be root n. But if you take k to be less than root n, you should still get a collision with probability k squared over n, which is true. And what this does is it's very permissive. It says you take k to be like 10 root n, so you're overwhelmingly likely to have a collision. And then if you do have a collision, there's a bunch of further tests you do. But if you don't have a collision, you're very forgiving. You just accept anyway. So the modification would just be strict. If you don't find a collision, you reject right then. And then the good state should, the yes instance should still have an advantage over the no instance. That's the sort of rough intuition. It's unclear if the details work. If you think of this as a proof system, there's a lot of ways to cheat these proofs. And the details of this involve going into the bowels of this paper. It's nothing terribly complicated. It's just a lot of epsilons. So let me say one.
To epsilon every time.
Yeah, they multiply and they add up. And then the worst is when you take the square root of epsilon.
Yeah.
Eighth root of epsilon. OK, so these are all hardness results. What about algorithms? So, I mean, that would be, I think, quite exciting. So it's nice to get a quantum reason why this basic problem is hard. It'd be another thing to have a quantum derivation of a classical algorithm. That would be pretty cool, too. And that's what this other paper, 1010.1750, otherwise known as Faithful Squashed Entanglement, which does not sound like an algorithms paper. It's by Brandau, Christandel, and Yard, quantum people you probably haven't heard of. And what they show is the following, that, OK, so actually, let me say a little bit more about this. Suppose, if you could do this in poly time, you could do 3-sat in time 2 to the root n. But suppose h sep squared of n plus or minus epsilon. Suppose you could solve this in time polynomial in this quantity here. Then you could solve 3-sat in time 2 to the root n. Now suppose, let's rescale. So now this is size n. Suppose you can solve this in time f of n. So we know if f of n is poly n, you get this thing. In general, this means that you can solve 3-sat n in time f of exp of root n polylog n. So if f is polynomial, this is the other situation. But then you can say, well, how large should f be because of this? And this argument says, if you think 3-sat takes exponential time, then f of n should be bigger than exp log squared n. Or in other words, n to the log n, modulo some polylogs, which I won't write down. Tilde. So now these guys, Brandau, Christanel, and Yard, gave an algorithm with this runtime. Yeah, it's do almost what we want. So let me write it down. So what they get is, well, not quite. Let me say what they do. So they compute h sep squared n of b plus or minus epsilon in time exp log squared n over epsilon squared. But there's a big asterisk. Yes, exactly. So b, of course, should be in this parameter range. But b also has to be what's called a quantum. B has to correspond to a quantum measurement. Quantum measurements always have this form. But b has to further have the property that it can be achieved with local operations and classical communication between two parties. So one way of saying this is that b should be of the form sum over I xi tensor yi, where the xi's are all non-negative. They add up to the identity. And the yi's are anywhere between 0 and identity. You could think of this as one side does a measurement corresponding to xi, sends the outcome to the other side who does a binary measurement. There's actually, that's one round of communication. For many rounds, what you could say is that b, here's a more general setting. b is of the form sum over ij root xi tensor root yi times bij times root xi tensor root yi, where xi and yi are non-negative. Sorry, this is yj. And they sum to identity. And the bij's are each recursively of this form or their identity. So that's the sort of most general class of things that they cover. So it's a general class of things, but it's not fully general. On the other hand, our reduction gives you not a fully general b either. So if you want to match our reduction, you don't need to simulate the most general possible b. But the b you need to simulate, so hardness is for b of the form sum over I xi tensor yi, where these are just any positive operators. So there's a sort of a gulf between these two types of b's. I feel this runtime, there's some evidence that this is the right runtime. But we can restrict b. We can show that for a general b, it's enough to solve it for b of this form. And this form looks kind of similar, but it's not quite the same. This is somewhat, corresponds to one round of communication. This corresponds to many rounds of communication. And these are measurements that cannot create entanglement, but we know that some of these are, it's a more general class. So one big open problem I'd like to resolve is to close this gulf. And it's not a gulf of completeness soundness parameters, but of the types of b's that can be simulated. And another open problem, which I have not thought about for very long at all, but I think is nice, is to see whether the parameters that are good enough for planted clique are also good enough for 3-sat, which would, I guess, sort of close the door on one approach. But on the other hand, it would say that these tensors, if we can reduce back and forth between tensors and 3-sat problems, then maybe tensors are not a beast of their own, but they fit more naturally into existing hardness. That's it. Any questions?
So you're not saying that this doesn't give another algorithm to planted clique in e to the log squared n?
It doesn't, because we don't know that the matrices, the tensors they construct are of the right form.
So the simple enumeration algorithm is exactly e to the log squared n. So the quasi.
If the clique is size 2 log n.
Right, for the random graph, which is, you see, the point.
Oh, right, because you only need to beat, yeah.
For the random graph, the point is that you only need to beat the 2 log n.
Right, I see. Yeah. So if my conjecture held, no, it wouldn't even then, because the problem is, if my conjecture held, then you could get a constant additive error. But that's not enough to distinguish these. So it's possible that if this conjecture holds, and you further modify this tensor, because basically you've got these like big eigenvalues. If you can somehow truncate those without screwing up the completeness. So if 2 big modifications held, then this would give another algorithm which matched the trivial algorithm. Yeah, I guess it's not. Yeah. So for cliques, I'm more on the negative. Basically, my thoughts for cliques are on the negative side, but for the other problem is.
Would there be a way to get a negative result for clique somehow, showing that if you could solve planted clique, then you could.
Oh yeah.
Some tensors, and then you could get 3-sat. So.
Yeah, so that's a great question. So the question, I guess you could say, how much of their reduction can you run backwards? So maybe a general tensor already kind of looks a little bit like their form, and the hard part of it is sort of clique-like. Yeah, that would be great. I haven't thought about that too much. I mean, I thought about it like very briefly, and it looks like the tensors that they have are of a very specific form.
When Bela Bolovash was here, he was saying he expects that planted clique should be easy for any clique of size n to the epsilon.
He also thinks P equals 10
What? No.
That's what he said.
Yeah, so.
That's what he told me. I'm serious.
But maybe he believes these to different extents.
No, I'm being
It was a
serious.
provocation. Okay.
So if.
Yeah, I don't subscribe to either of those beliefs.
Well, if you strongly disbelieve that, yeah, so if you believe the exponential time hypothesis, and so for 3-sat, then, yeah, if you could show that general tensor problems could be reduced to planted clique, that would be some pretty strong evidence that planted clique is hard.
But planted clique for random graphs, we know it's into the log n is
Upper bound.
and upper bound. So.
Yeah, so it can't be that hard. Yeah, so it's yeah, that's basically you can think about these reductions in either direction. It'd be very interesting if the general difficulty of and I guess one thing that's nice about this is the question of what values of B what choices of B do you allow? And I think one lesson is that if you allow fully general B, you get stuck earlier. And so just to show that there's some large class of B that reduces to finding a clique, I think would be quite nice.
But one thing that just this construction suggests is maybe you could try, by recursitivity, approach planted clique by building some huge matrix, you know,
Yeah.
but still
Maybe n to the log n or something. Yeah.
No, but you know, I want still polynomial size matrix, like n
Yeah.
to the 10 by n to the 10, where which you build in some sophisticated way by looking at triangles or
Yeah.
paths of length 10 in a graph. And the eigenvalues of this matrix will tell you something.
Yeah, in fact, the way this thing works is it reduces this problem to a matrix of this size and finds the largest eigenvalue of that matrix. And there's a... Yeah, so...
This just runs the STP. It's kind of like the Watcher's thing.
What's the Watcher's thing?
What you first proved, like three methods.
Oh, it's simpler than that. Simpler. They actually, they sometimes describe their thing as an STP, but it's just a largest eigenvalue problem.
What STP is?
Well, sometimes you have to do more work for it to solve an STP. Yeah, no, it's simpler. I think it's simpler than that Watcher's thing, as far as I understand the Watcher's thing. It's, yeah, maybe another time I can describe what their algorithm is. It's pretty simple. It's just the analysis of it that's tricky.
I think